Hey guys, we're getting really close to the end of this course. I left off at the harmonic functions in chapter 6, and then comes the a strange form of the mean value theorem and a maximum principle. We're not going to cover that. Now we're beginning chapter 7 on power series. Now it turns out that the extension from the reals up into the complexes makes almost everything in power series exactly the same. And so I'm going to rapidly do a couple of things here, but what I'm going to talk about first is we have a focus, and that is turns out integration is really kind of neat in that how it allows us to integrate over contours, and these contours allow us to do infinite integrals and quickly get answers. There's a standard technique that is going to be used now, and that is this technique is going to reduce everything to a series of one form or another. And you guys are very used to what is called a simple power series. But it turns out simple power series are not enough. We need to actually, just like we generalize the reals into the complexes, we're going to generalize the concept of a power series. It's going to become something more. Now, in order to do that, the general ideas of power series need to be known to us, and we have to do a couple of tricks. And if you remember from calculus, we had lots of tricks, and the most standard one was this one. From this geometric series, you ended up getting this series, and then you got this series, and then you integrated it, and you got this series. And you could create tons of series. It was a very interesting little process. It was called the algebra and calculus of series. But then a guy by the name of Maclaurin and Taylor showed up. I'm a big believer that Maclaurin had an L, no space here, but L-A-U-R-I-N. And Taylor and Maclaurin decided, I'm not going to figure out a series and what it represents. Instead, I'd like to have a function and find the series for it. And what's really strange here is that integration is going to be the way that we come about and understand Taylor series. And Taylor series is going to work out just wonderfully. So our focus is maybe doing something like this. E to the z over sine of z integrated over some contour that's funky that probably includes a couple of zeros of the sine function. And this one, it doesn't have the right form. We don't have that z minus w in the bottom. We have a function that's 0 for a different reason. So why is it this was so special? And that's what we're going to search and try to find out. Now, in order to get to where we're going, it turns out there is one very special form of series that you probably studied in real analysis, and I'm going to draw a function here that's not too bad. I'm going to go from 0 to 1 over n. It's going to be 0 there, and then it's going to instantaneously jump up to 1 over to 1, and we'll make it there and 0 here. This is my function f sub n of x. For every n, we have a function. Now, it turns out that if you let n go to infinity, you have a sequence of functions that become more and more and more and more and more that look like this function. Just like the function that is 0 at 0 and then 1 everywhere else. That's where it's, quote, converging to as a function. So f sub n of x as n goes to infinity is converging to this function. That's not a very nice convergence. I want to show you a better convergence. Suppose I had a function that looked like this. Let's just take the function y equals 1 plus 1 over n on 0 to infinity. So here's y1, which is at 2, and then y2, which is at 3 halves. This is a sequence of functions that's getting closer and closer to 0 to infinity of a height of 1. But it's getting very nicely at every point x, it's about the same distance away. Why, here, in this one, there are some values of x that are a very long way from where they're going to end up, no matter which n you're at. You pick an n, there's some x's that are way away from their final value. Well, in this picture, there's the x's where the y's are all very, very close. But for this n, that y value is a full distance 1 away. We say that this one is converging uniformly, that it's being squeezed nicely, very, very closely, and that once you get close with some of x's, you're close with the others for the right choice of n. That's called uniform convergence. It's a very kind of nitpicky process, but it turns out it's really important and something that we want to do. Uniform convergence is going to allow us, when a series uniformly converges, it's going to allow us to switch the summation of an integral and the integral of the sum. And that's the only thing we're going to be using it for. So we're not going to worry about how series are talked about or how sequences are talked about. We're just going to talk about a sequence of functions, and we're going to say they converge uniformly, and it gives us two little theorems. So I'm going to write those theorems down. The first is proposition 727. If you have a sequence of functions in the complex plane, and they're continuous, we want bad functions, and f sub n converges uniformly to f, which is also g into there, and gamma is a contour in G, then first thing we can do is we can move the limit inside the integral. But the limit of these things are G. It's F. So the first theorem is that when you have a uniform convergence of functions getting close to something else, then limits and integrals are interchangeable. Super, super powerful fact. Now, the next thing that we want to talk about is we want to talk about intervals of convergence. So let's look at our favorite series, or rather Dr. Sorensen's favorite series, the geometric series in the complex plane. Now, it's not hard to prove that this converges for the norm of c less than 1. So it converges in a very nice region. That means that this function is represented by this series super nicely. Now, in regards to this concept of uniform converges, well, it turns out that most of the series that we're going to look at are going to look like geometric series or look like Taylor series. So I'm going to state the first theorem about these guys, and that is, if you have a power series, so you have a complex power series, then there exists a real number R so that this converges. And so now, not only does this converge on some radius, it absolutely converges, which means we can throw in absolute values. And it gets better than this. If little r is strictly less than this capital R, then it converges uniformly on the disk centered at z naught of radius r, which is inside of the disk centered at z naught radius big R. In other words, the convergence behaves very nicely. For every z, the control of the convergence is the same. All right. So we have radius of convergence. We have really nice convergence. We're inside the radius. Now, there's something strange that this says. This says that when you actually have convergence in the complex plane, the convergence is nicer than convergence in the reals. It becomes absolutely convergent. So things are somehow much better. Now, how in the world is this going to help us? Well, it's going to help us in a significant way because we're going to develop Taylor series and Laurent series. And Laurent is this new generalized series that's kind of neat. Again, the focus, now we're at chapter 8, actually. The focus is still kind of understanding the exponential of z over the sine of z dz over some path that probably contains zeros of the sine function, so that's some trouble. So what we'd like to do is we'd like to develop the idea of Taylor series from the complex point of view. We're going to develop in the same way that we developed it in reals. Suppose you have a series and because of our form, let's say that this is convergent on some disk centered at z naught of radius r. Well, that means for all the values inside of the disk, this is representing a function f of z. Well, what kind of function is it? Well, this function is a really nice function. Then f of z is holomorphic in this disk. In other words, it's a differentiable, very nice function. Now, you should remember that from calculus. The minute you had a series and it converged, you started doing its derivatives. And as soon as it started doing its derivatives, you started doing its integrals, and you use series to create other ones. So all of this theorem is saying right here is that series are behaving just like in the real world, and that is when you have a series, you can differentiate it, and you can take the integral of it. These are really nice facts to have. Well, since we claim that that's doable, then we should tell you what the derivative is. Well, the derivative, with that other theorem, with us doing limits, allowed us to pull the limits inside, and that the derivative then is the sum it is the term-by-term differentiation. However, this is infinitely long. Doing term-by-term differentiation is not a trivial proof, and I really doubt that in Calc 1 or reals, you guys got to see that, or in Calc 2. So how are we going to prove that you can do an infinite number of derivatives in the complexes? So let's attempt to do a proof. So we're going to start with z in our disk. So we have the z minus z naught is less than r. Now, we want to choose a smaller r because we get uniform convergence. So just think of here's your g and here's your naught and there's this r. Let's take a slightly smaller one. So let's pick an r1 smaller than r, so we have z minus z naught is less than r1, which is strictly less than r. Now, why can we do it? Because we're not equal to r, so that when you pick something, this is that topological idea, remember? There's always a disk that gives us space, and since we're not on the edge of the disk, then there's another disk. This is what we're doing. We're getting small enough. Now, what are we going to do? Well, we have Cauchy's integral formula from the very beginning of chapter 5 that says that the derivative of a function is 1 over 2 pi I times the integral over some path gamma of f of w, z minus w squared dw. All right, so, well, f is our series, right? So that's what I want to plug in here. Just going to write sum over k. And, okay, this is using w, so I'm replacing the z in my series with the w, but I still have z naught, so it looks like I'm doing something fishy here, but it's not. And it doesn't matter the order that we write this. So now, the trick that we're going to do is the following. What we're going to do is we're going to want to take the sum and the integral to switch them, and we can do this because of the absolute convergence. And so now we have 1 over 2 pi I. Take a sum, and the sum is k equals 0 to infinity. The ck comes out in front, and then we have the integral of each one of these terms, w minus z naught to the k over w minus z squared dw over some gamma. Now, what we just need to observe here is that this is the derivative of w minus z naught. So, and this then gives us and so we have arrived at what the derivative of the function must look like. Now, that's really cool. We've just proved that by having absolute convergence, we could switch integration and summation, and that allows us to say that we can do infinite differentiation term by term. So, we can identify some series now. For example, f of z. If we write down z to the k over k factorial, k equals 0 to infinity, that's clearly the generalization of e to the z in the complexes. But now that we have term by term differentiation, it is itself. Take the derivative, that's the answer you get. So we have f of z prime is equal to f of z. So that's interesting. So let's take a look at the following. We can take a look at the derivative of our function f of z over our known exponential function of z. You guys know how to use the quotient rule, right? Well, let's do the product rule, much easier. Well, derivative of the first times the second plus the derivative of the second times the first. But this is that. F of z is f prime of z. And so this is 0. So what complex function's derivative is 0? Well, that complex function's derivative is 0. There's got to be a constant. So f of z over the exponential function is a constant. So f of z is some constant times e to the z. And now we can evaluate it and discover what that constant must be. You know what it is? It's 1. F of z up here is our exponential function e to the z. But we built it from a series. Well, let's still keep doing that. Those are good ideas. Let's build series and see what we come up with. So we have our sine of z. We know the definition of that. That's 1 over 2i, the exponential function of I, z, minus the exponential function of minus I, z. And guess what we're going to do? We're going to plug in our series, walk through them, and you know what we're going to come up with? We're going to come up with exactly what we saw in the real plane. So what do you think that every series that we had in the reals extends to the complexes? And the answer is, you bet they do. There's not a single exception amongst that mix there. So now we have a lot of series that we can claim to know. Cosine of z, sine of z, e to the z, log of z around different points, but we're not there quite with that one there. That gets a little bit harder. So now what we'd like to do is we'd like to know, how did Taylor come up with Taylor series? I bet you didn't see the proof of it in calculus, and some people in real analysis make sure they go through, but it's often glossed over. Why? Because the best proof makes your use of complex analysis. So here we go. Suppose we have a function f of z, and it's holomorphic, differentiable in a region then here's the cool fact. I want to say Taylor's theorem, but I'm not going to give Taylor's theorem in the way that you expected. Then f of z is equal to a series of z minus z naught to the k equals 0 to infinity, for z naught an element of G, so you can do it at any point, and there's a radius of convergence up to a value r, where the disk fits inside of G. Now, that's really interesting, but it hasn't told us how we find the constant. So now our CKs are going to be 1 over 2 pi I, the integral over gamma of f of w over w minus z naught to the k plus 1 dw. Now, those of you that saw chapter 1, that our integral with the 1 in, chapter 4, our integral with 1 in the bottom produced a nice answer. When it had 2 in the bottom, it was actually the derivative. Turns out when it's 3 in the bottom, it's 1 over pi I, but it's the second derivative. It turns out that this is Taylor's formula. This is the nth derivative divided by k factorial. And we're going to end up proving that. And this is for some gamma that's orientated, positively looped around z naught in this region which lives inside of G. All right, picture G inside of the complex plane, z naught. There is a Taylor series that converges in that region, and all we have to do is find some gamma within that region, preferably a circle center at smaller than r, that calculates each of the coefficients. All right. Seems like this shouldn't be too hard to prove, because we've seen that these things have some very nice properties. All right. So we're going to begin by defining our function shifted over. So we have this f of z. We have this z naught in G. And what we're going to do is we're going to define g of z to be f of z plus z naught. That way, when you plug in 0 here, it's f of z naught. And by the time you hit the radius of r there, you've come out. And so this allows G to basically be f-centered at 0. And so G is holomorphic on D of 0, comma, and it can still use that big R. And Z naught is inside of some gamma that we may need to draw a picture of. Now, since G is holomorphic, that means Cauchy's integral theorem applies, and values of G can be calculated by 1 over 2 pi I times that G of W over Z minus W dw over this gamma. And the gamma we're going to pick here is the circle centered of radius at 0 with some small r where the r is going to be chosen less than that big R. Okay? Now, we're going to be slightly tricky here. And this trick we're going to use time and time again. It turns out that when you're working with the geometric series, that's what that really is, there's two things we can do here, two algebraic tricks. One is we can make it read like 1 minus z, and the other is that we can make it read like a specific number plus, let me just show you the trick. So first off, if I divide by w here, I can make this read 1 and factor out w, so pull out w and I have z over w minus 1. That's our first trick that we can use. I think I want it the other way around. I wanted w minus z, sorry. Pull out the w, and I get 1 minus z over w. And so that's 1 over w times 1 over 1 minus z over w. Now that's the geometric series with this being the terms. And so this is 1 over w times the sum of k, not k, z over w to the k power k equals 0 to infinity. So when I see a w minus z, there was the source of my trouble right there. I didn't write this correctly here. This should be w minus z. I changed the roles of w and z here. Normally w is the end, z was in the front. Since w is the value here, I put gz. That's how it got written strange, and that's the mistake I made there. We normally wrote it the other way, but I have w as the variable, so z is the one that goes in front, and that's why we needed to write it this way. So now, with this fact, I can plug that into here. All right, so now I have got this sum inside of an integral. Since this, again, converges uniformly, this is a theorem that we need, I can switch the order, and I get the sum on the outside. And I can put of course, I can move the 1 over 2 pi I through. But now this will be the integral of gw over w to the k plus 1 dw over gamma. So all of those get pulled inside of there. And there's a z to the k here. That has nothing to do with that derivative, that integral. Well, this is just a different form of an integral that we've seen before. If I make the right substitution, and so I can now go back to the strange fact that f of z is really g of z minus z naught, and I can do a linear substitution here of changing z to z naught. That's all I'm doing. I'm going to change z to z naught. And I'm going to do a linear substitution for the w in here, as w equals z minus z naught as well. So therefore the derivative of w will be the derivative of z, and the g minus z naught will be f of z. This will be z minus z naught, and the w will be w minus z naught. So I'm going to make two linear substitutions. So the g I bring back to f of w. The w becomes w minus z naught, and it's to the k plus 1 power dw, and then the z was substituted as z minus z naught, shifted it back. Now that looks pretty funky. Doesn't that look awful familiar? What's the only difference here? The only difference here is what circle this is being done on. And this is exactly what the C sub k says that we said would happen. There's the z to the k, there's the C sub k's. So we just proved that theorem that when you have a function holomorphic, then it can be represented as a series, and all we have to do is figure out what these values are. Well, if you look at the beginning of chapter 5, and you iterate that, it turns out we know exactly what these values are. These values are the kth derivative of w divided by k factorial. So we've actually proved Taylor series, but we calculate their constant functions in the complex fashion using the Cauchy integral theorem. Now that we have Taylor's theorem, that means we can do all sorts of crazy things. But before we do some crazy things, one might want to ask, okay, why did Taylor's theorem have this strange presentation? Well, the answer was you always start with a function and you want to find the series. It turned out the valuation of a function was the answer to integrals. And it turned out that the derivative of the evaluation of function was equal to integrals. And so when integrals were introduced here, they were equivalent to the derivatives. So Taylor had discovered something very nice that was a very generalization in the complex plane. But one last important thing that is not at all obvious in the reals, and we're going to discover something really important here. If we have g living inside of the complex plane, and here's some z naught, and we have some function that's holomorphic here, then we just expand the largest possible disk in here to find a representation of the series. Now we can't go too far out because then the series will fail, which means that there could be another spot where there's a power series here that doesn't match the power series there and represents the function in greater places. And we may have to meld together many, many power series to describe this function everywhere. But we have all of these series that represent it. So it really is strange. It really is strange in the complex world. But it says something about the real world we didn't see coming. 1 over 1 plus x squared. I wrote down a series from that earlier on. That is 1 minus x substituted with x squared. So it's minus 1 to the power. And it's x to the even powers. And n starts at 0 and goes to infinity. But this radius of convergence, when you look at this in the reals, is just x less than 1. Why? Well, here's the answer. Let's look at 1 over 1 plus z squared. And then observe that that function is very nice in the complexes except at I and minus I. So when we looked at the real plane and said, where does our series converge? Well, let's look at the complex plane. This function is holomorphic. What is the largest disk centered at 0? Well, that disk will come up and hit right at I and minus I, and that's where the we lose holomorphism. So guess what? This is the disk very clearly by this theorem. Expand to the edge of holomorphism to know where this convergence happens. We didn't know why our series 1 over 1 plus x squared wouldn't converge for larger values, but now in the complex plane it clearly points out why. The region of holomorphism for this function fails centered at 0 when you finally hit I. And so when you look at the disk of radius 1 in the complex and restrict it to the reals, lo and behold, in the reals, the interval is from -1 to 1, which looks like everything should be good in there. That's a very, very powerful statement. Right. So now we have all of our Taylor series that we've known before. We have reasons that some of these Taylor series have convergence. And so now we are ready to ask, how do we generalize our series? So my next talk will be on Laurent, starting on page